So today we're talking about cryptography. I honestly enjoyed this part of the book a lot. I really did. Maybe it's the math nerd inside of me. But there is gonna be a bit of math, but I will do my absolute best to explain it in a way that isn't too crazy. And obviously I'm not gonna go fully in depth in everything about it because it's a lot more complicated than I am qualified to teach. But I'll tell you guys the basics. So kind of like the overview, we'll go over private and public keys, elliptic curve, cryptography hash functions, and we'll talk about Ethereum addresses, just kind of how you get to that, kind of just to show you guys what happened in the background, what MetaMask was doing for you. And then we'll walk through today for the Solidity 101, we'll walk through different value types, functions, and variables. And then last, the activity for today is gonna be a decrypting challenge. So what I'm gonna do is break you guys up into teams, and you're going to come up with your own hash function, and you're gonna give a couple examples, and you're gonna put it on the Jamboard, and then what everyone else is gonna do after, it's gonna be 10 minutes to do that, and the next 10 minutes is gonna be you guys trying to practically break people's hash functions and see if you can figure it out. So hopefully that is fun. But if you haven't already, mentioned hackathon, make sure you participate in it. Yeah, just really cool opportunity. You don't have to have your project done. We're not expecting any of that. We're all super busy, but we do obviously work on it, get some done. Maybe if you can get a demo of like the core functionalities, that'd be great. But yeah, it's mainly gonna be just kind of presenting what the idea is. So, sorry, I see someone's taking a picture. But yeah, go ahead. This is the sign up form. I want to do that. I'll give you guys like 5 seconds. I don't see anyone. Okay, we don't have to. So enough time killed. All right, so keys and addresses. So what is like the relation with keys and address? So last week we actually got you guys to sign up and get a wallet, and you saw like at the top of your wallet it showed like this hexadecimal number. And if you don't know what hexadecimal is, it was whatever number that looked like 5, 4. So a lot of stuff like that. So that is your address, but your address actually comes from your public key, and your public key actually comes from your private key. So it's kind of like it has to go through these different steps in order for you to actually get your address. But the beauty of cryptography and what makes all blockchains really just kind of incredible is the fact that although your address comes from your public key, which comes from your private key, you can't go backwards. So just because you give someone your address, that doesn't mean they're ever gonna know your private key. And your private key is what is, like I mentioned before, it's what actually allows you to control and access your funds. And if you lose it, it kind of sucks. Like I said, your private key is super important because it's what allows you to access, control funds, and do digital signatures. So in order for like a transaction on any blockchain to be valid, you have to have a signature on it. It's just like when you go to the bank, you write a check, you got to make sure you have a signature, or they're not going to know. They're going to be like, well, anyone could have just, written up this check and wrote a fake signature. Do they actually check your signature? I don't really know. They probably do. But that's essentially what your private key is. But your private key allows you to have these digital signatures. We'll go more into depth about digital signatures in like 2 weeks. But we're going to talk about public key cryptography. So public keys are private keys. Sorry, public keys. Yeah. So uses. I literally forgot what I even wrote. But your public key is a unique identifier of like who you are, what exactly. It's kind of like the way you can think about it is like your bank account number. And the way this is derived is from math, is using some pretty complicated math that, like I mentioned before, is you can go one way with that math function. So the way I'll think about it is like, think about any function like 2x plus y, right? You put in the some number x, which would be like your private key, and you'll get an output, and that'll be your public key, and then you'll do that again, and then you'll get your address. And so, but this is a unique identifier, and the beauty of it is no one can derive your private key from your public key, and I'll talk more about it. But some special properties, like I mentioned before, is that it's really hard to inverse it. So you could, like, potentially, if you gave someone your public key, if someone knows your public key, they know your address, they could figure out what your private key is. The only thing is they would have to go through a bunch of they would have to try every single possibility. So if you're familiar with kind of like leak coding or anything like, or maybe just computer science in general, you know the term brute force, where you have to just try a bunch of these different practically inputs to try to get the correct output. But the thing is, there's 2 to the power of 256 different possibilities, which is, let me tell you, there's about what I think is like there's close to as many possibilities of inputs you can try for your private key as there is atoms in like the universe. It's actually kind of insane. So it's going to be really hard for someone to go through it, and most computers nowadays are not really there yet. So, but this is known as asymmetric cryptography. Like I've been repeating over and over again, is where you can derive your public key from your private key, but no one can derive your private key using your public key. And I'll go more in depth about that. But an example just to maybe get it through, because a lot of this is kind of repetitive, but it's really cool once we actually get into the math. But so this is an example called prime factorization. So given two large prime numbers, like it's pretty difficult to find the prime factors. So if I tell you like, here's a number 8,018,009, like could you find the product, like those two prime factors? It's kind of hard, right? But if I told you like, hey, one of the factors was 2,300, or sorry, 2003, then it'd be really simple, because you could just divide that number, use 2,000 whatever, and divide it over 8 million, and you'll get the other prime factor. And this is known as like a trapdoor function, where you can go one way. You go one way really easy in finding the 8 million, but to go backwards to figure out those prime factors is really difficult. But if you know one piece of information, like one of the factors, it becomes really difficult. So this is just an example of like a form of cryptographic function. But obviously, like I was stressing before, you actually can't go backwards with the type of cryptography they use on all the different blockchains. So this was a really bad one. So what they decided to use is something a lot more complicated called an elliptic curve cryptography. And this is where things get really, really interesting, in my opinion. So with elliptic curve cryptography, there's arithmetic like you can do with normal, integer numbers, but it's also different because you're working with points on a graph. Because essentially, like what we did with the prime factors, like you just took these integers and there wasn't like a constraint on them or anything. But with elliptic curve, you're specifically only using points that are on this graph. So there is constraints, and also because you're using points, you can't do division. So you can multiply, but you can't do division. And we'll talk a lot more about this, but this is like the basis of like the foundation of what Ethereum, Bitcoin, and all of them use in order to actually create like your private key and use that to get your public key and digital signatures as well. So private keys. Your private keys are actually a lot simpler. To get your private key is not that much. Your private key is simply just picking like a random number. And like I mentioned, this is how you actually prove that you own your account and you actually are able to access your funds, because if you want to send money, you need to write a digital signature. And in order to write a digital signature, you need your private key. But it's actually really simple to get your private key. Like when we set up your wallet last week, all MetaMask really did was just use some random number generator and really get you this number. But the most important, the first step is having a really good source of randomness, or what they call entropy for those in physics. And this is important because if it's not like, there's a bunch, like you've ever used like those random number calculators online or something like that. Like those are actually really bad because someone had to like kind of write them, and they're kind of predictable, more predictable than you would think. So there's a lot of different ways. There's a lot of more like secure ways you can do it. We won't go too deep into that, but essentially you're picking the random number, and this number has to be between 1 and 2 to the power of 256. And so this is a huge digit. It's about 79. It's, what is it, 70-digit number, a 79-digit number. So you can just imagine 79 numbers. I don't even know how big that is, but I think what I saw was an interesting fact. Like I mentioned, there's close to about as many atoms in the universe than there is options for private keys. So you don't ever have to worry about, oh, like what if I pick the same number as someone else? Well, if you use a good some form of randomness, if you use a good source of randomness, then you won't actually have to worry about that, because there's just too many options for the probability of you actually picking the same private key. But again, all of this is, you don't ever actually have to worry about this. MetaMask did all of this in the background, but if you yourself want to program a wallet, then this is something you'd have to keep track of. And this is completely all offline. Like you can do this completely offline, so you never actually have to go online if you wanted to. So your private key is 256 bits. If you wanted to, you could get a coin. You could get a coin and flip it 256 times, and that's actually a pretty good source of randomness, because There's no one really, wrote the coin. You're not going to control gravity or anything like that. So, but all this can be done off the network. You don't have to be connected to the internet. Definitely do not want to be connected to Ethereum. And important thing to know is like your private key does not travel across the Ethereum network. And so public keys, this is where things get a lot more interesting. So your public key is just a point on the elliptic curve, meaning it is the set of x and y coordinates that satisfy the elliptic curve equation. And all that being said, it's really just the x and y combined, those values, whenever you go through the function. And so this is what an elliptic curve is, because you're probably wondering, like, I think I actually had a picture earlier, but this is what an elliptic curve looks like. And the function, and the specific elliptic curve function that Bitcoin and Ethereum use is called SECP256, and the formula is y to the power of 2 equals x to the power of 3 plus 7, and you'll usually get this graph. And so the difference, so what I have written up there is actually kind of incorrect, because it's this function over module like a finite number. So there's actually a finite number of points you can actually use. So this graph is drawn using all real numbers. So there's decimal places in there. But actually, this is limited. This actual function, SECP256, is actually limited to prime numbers and specific ones. So the curve, like I mentioned, the curve is a finite number of prime numbers, and Ethereum uses this specific elliptic curve formula. So it's not only just Bitcoin, they kind of just stole it from. It's not only just Ethereum, they kind of just stole it from Bitcoin. But this is actually what the graph looks like. So this is like over the domain of real numbers, and this is over the actual domain of those finite amount of prime numbers that you can use. And this gets really, really interesting. So now we're going to talk about the addition, and I'll draw an example on the blackboard. But so to actually, let me just focus on the arithmetic before I jump. So the arithmetic is pretty interesting. So whenever you're wanting to do addition on elliptic curve, let's say you have your point P. Where's my point? You have your point P. You have Q, right? So P plus Q equals R. That's what happens, and you simply are just drawing a line through P and Q. And then the thing about elliptic curves is when you're drawing a line between 2 points, you're always going to intersect another point. So there's going to be 3 points whenever you're drawing that line through the graph. And so what you get is that third point becomes R, but you have to invert it. You have to flip it across the x-axis in order to get the actual value of R. Now the reason why this is definitely way over my head, but so simple, like, what I found that they said is you need this reflection in order to make the addition associative. So those that don't know what associative is, you can do A plus B plus C, and it doesn't matter which ones you add first, it's going to get the same answer. So this is elliptic curve. This is addition using on the elliptic curve. Now, multiplication. We all know multiplication is just addition repeated over and over again. So, but with the elliptic curve, it's interesting. So you have P plus P, right? And that's essentially, you're just saying, I have this point P, and then I want to draw a line through P that connects P with P. Pushing P, I guess. But so you're going to draw a tangent line through this, and like I mentioned, if you're drawing a line through 2 points, you're going to get to a third. But if you're drawing a tangent line through just 1 point, you're only going to intersect at one additional point after that. So there's only going to be 2 points that your line is going to cross. And just how we did with R plus Q, if P equals Q, then you're drawing that tangent line, and then whichever the second point that you get to, you intersect that, you have to invert it, and then you're going to get to what actually your value is, which is 2P. So that's math. And so to think about it, simple way to think about it, K times P is just P, P plus P plus P, the summation of P to K. And division is not possible. And I really need to stress this, because this is what makes this function really secure, because I don't know if you guys have ever tried to actually divide decimals. It's a lot harder. Some of you math people might actually have done that before, I don't know, but it's not possible. It's really, really difficult. So this is actually the function that's used to generate your public key. To me, this is beautiful. Like, to think that you could have, to think that the public key that people use to kind of send you Bitcoin, which is your address, which is derived from your public key, is practically created, is found using this very simple formula. It looks really, really simple, but like I mentioned, what you're essentially doing is doing a bunch of elliptic curve addition. And so I actually want to draw this out. So if you have, let's say you have your point G, right? So the thing is, K is your public key, capital K, lowercase k is your private key, and then G is the generated point. It's a fixed point. It's a fixed point on the graph. And every time that a public key is made, everyone is using the same G. And obviously the difference is your private key. And like I said, doing K times G, K times P is just doing G a bunch of times. And like I said, you'll draw the line that's tangent to it, and then somewhere far up here, we'll cross the point, and then you'll get it there. Let me do a better example of that, so it's not as ugly. And so you'll get your point here. And then essentially what you would do again is then draw this tangent line, and then you'll get right here. And then you'll just do this over and over and over again, or whichever the equivalent of your private key actually is, whatever the decimal equivalent is. The beauty of this is, let's say your private key was like 10. You're doing 10 and G. So originally this will take like 10 steps if you're actually just doing it through the tangent. But because it is associative, you can look at this like it's G plus G plus G dot to 10, whatever that G is, and you can just actually go, I'm gonna do 2G first plus 8G, right? And then so what you're really doing is whatever, let's say this is like the result, the point you get after you've done this tangent addition twice, then this is the point you get after you've done it 8 times for some reason. Then all you really have to do is then draw this point, draw a line through these 2 points, and then you actually save the amount of like computation of steps. Is anyone confused about that? I might have gone through that fast. A little bit. Any questions though? So, but the reason why I want to walk through that, because this is a really efficient cryptographic function, because you're able to save the amount of steps that it takes to actually compute this through just kind of doing pretty interesting math. And I did this kind of weird, because it's really what you would do is like you'll do 2G, then you'll do the next 2G, and then you do that over and over again. But this is a really beautiful function, really beautiful formula. This is the math. Is there any? Yes, sir.
So is this slope G, like is that G, or why does this slope matter? Or why does the line matter?
The line, this is just a geometric way of actually kind of looking at it and doing the addition. But really what you would be calculating is that slope of the tangent. And so, but that's a lot uglier to do whenever, this is what a computer actually works with. So they're not drawing any lines, they're just like figuring out like this point and this point. Does that answer your question?
Okay. Oh, so like I get like 2G and 8G, and that's how you get G, right? So is that the point that we originally started with? Is that what you're trying to say? Like
Yeah.
That dot right there. The one that you did on the left side right there?
This one?
Yeah.
So this is your original G.
And that tangent line is the one that we want.
Yeah, and this is not a tangent line at all. I just realized.
Oh yeah. I mean the one that you drew earlier, it was tangent.
Yeah.
Yeah.
And what about that? Sorry.
No, because never mind. I was thinking like, the 10G, I get why the 10G matters, but I didn't get why the line between the 2G and the 8G matters.
Oh, okay. Because, sorry, I didn't explain that well. What I was saying is like, so once you do G and G, right? Because G and G is just drawing that tangent line. And then you could take that point, you could take what 2G is, and then, so like your 2G is here, and then to add another G to it, you would then draw another tangent line at where 2G is, right? But so instead of doing that, the way you could think about it is you would have another, like you'll do another G here, like you'll do this by itself because since it's associative, and that'll get you like another point somewhere here, let's say just randomly, and then you can just actually do the previous addition because those two points on the graph are not the same. if that makes sense.
Okay.
Yeah, so sorry if that was a really bad explanation, but that's essentially what this formula is doing. It's just taking G and then adding it to itself, which is really, if the simplest way to think about it is that you're doing a tangent line at different points that you're getting on the elliptic curve graph. And yeah, like everything I just mentioned, kind of the properties is, so like I said, you're taking G multiplying by itself K times, and then you can't divide this. Just off of that, I don't really know how you kind of divide. And last is like I said, all private keys are derived from the same G, and so every time that you use the same private key, you should always get the same public key, but it's not invertible because you can't divide. Yeah. And is there any other questions on that?
What exactly is G? Is that just like a regular coordinate point, or is that like the slope of the tangent?
Yeah, great question. That's a point on the graph. I'm sorry. Yeah, G, like I said, K is a point on the graph. So your public key is, like we said at the beginning, is a point on the elliptic curve, and G is just a generator point. So it's this point that they arbitrarily decided, like, this is going to be the point that we all use to derive to get someone's public key. Good question. Any other one?
Is there like I don't know, specific guideline that you use for designating a G?
For like picking the G, or
It's just random.
no, it's specifically picked. So there's that library. So SECP 256 that will have like, there's already like a predetermined G that the kind of like the whole community decided on.
If you're new to the generator points, could you then like go backwards and not like divide, but use the same elliptic like subtraction and then go backwards and find the private key? Or is that like not possible either?
That's a good question. That's not possible. With subtracting, because you can't, because essentially what subtraction is no, yeah, it's different because, like I mentioned, I didn't even do that correctly. The reason why I was getting really stuck because I realized when I did this G and you get to 2G, you have to invert. So you actually won't be like drawing a tangent line at the same place. Like that's why you can do this. You can do like 2G and 2G because you're inverting. So it's actually going to be at a different location. So yeah, no, you can't divide. You can't like just subtract because when you invert, then you're actually at a different point in the graph and like it's going to end up somewhere else. And I'm not about to walk through that math because that's really nasty.
Well, could you still like, I guess go backwards in the process if you use like the generator point?
Well, yeah, no, you could. The thing is, you would have to know K. So you'd have to know the amount of times you actually need to go back. You need to subtract to go backwards, which is why we say like you don't tell anyone your private key, because if they know your private key, they just use that formula and then they can get it. But if you don't know the person's private key and you only know G because everyone knows G and you know their public key, like the only way to actually do that is to divide. You can't really subtract, and you can subtract arbitrarily, but that's going back to using the brute force to trying to find the public key. And if there's 2 to the power 256 possibilities, that's a lot of computation you're spending.
Wait, so is this a standard hash function? Like, is it used for things other than crypto?
Yeah, it's used like I can't remember all the places, but it's like the most prominent cryptographic function out there. Because if you guys have ever heard of what is it, RSA, that's a really popular one. But this is even better. Like it would take I think about 3,000 keys to get as much security as if you only had like I think it was 64 bits. It'll take a 3,000 bit key compared to a 64-bit key using the elliptic curve. So it's this is a lot more efficient. Any other questions? Okay. The cryptographic hash function is not as much. There's just some words, and I'm almost done here. So I'm keeping my promise. So a hash function. So essentially, what I showed you is that was a hash function. That was a hash function. Just a lot, like really complicated, complex one. But obviously, it has to be that way in order to be secure. And a hash function is just any function that you can take an arbitrary amount of data, and then you do that algorithm on it, and then you get a fixed data. And I'm going to show you guys an example. So let's say we have this hash function, just some whatever hash function it is, and you input in your input is high, and so what they call your input is called like the pre-image, but we're going to call it the message. That's the term we're going to use. And high, and then the hash function this is a really simple hash function. Take the first letter of whatever the message is, and so you end up with just H. So that is a hash function. You could do that as well. And there's other ones you can do, like shifted like 8 times or something, and whatever. So you could do a lot of creative things, and that's what you guys are going to do after this. But this is another example, kind of a more realistic hash function where they're taking whatever the message is, running it through whatever algorithm they decided, and then you get all these different like inputs that they map to. So this is like I said, it can be, it can be an arbitrary size, but you always want to end up with the same, just because you don't want anyone to be able to easily tell what the image was. Because a good hash function is invertible, like I mentioned before, like the elliptic graph. It's always going to be the same output, same size. So the input could be a million letters. It could be like you could put a whole essay into the hash function, and you should still come out with the same size output or hash. And just please raise your hand if you have any questions about anything.
Sorry, where does the seed phrase come in?
The seed phrase?
Yeah.
So the seed phrase, great question. The seed phrase is just a representation of your private key. So like your private key is 64 bits, and all the seed phrase did was kind of like map these words to that 64 bits, so you don't actually have to remember 64 different digits and actually input that. Yeah. Questions? Good question though. And so the properties of a hash function is determinism. So that means that if you put the same input, you should always get the same output. Verifiability, and what does that actually mean? Forgot. Computing is efficient. That's what I thought it meant. But computing it is actually efficient. And this is a really important part of crypto and blockchain, is because data on the blockchains aren't actually like put through any like hash function, but whenever you're doing like your digital signature and you're getting your public key, that's put through it. But what you're doing, the reason why you want it to be very efficient to verify it is because it'll take a lot of work for you to maybe get the correct output that you want, but it's very easy to check someone's work. And because you know the correct output, you know what the correct input that they use, so you just plug that into the hash function. And this is really relevant when it comes to proof of work, and we'll talk about that later. If I didn't make any sense, we'll 100% talk about that. Non-correlation, so meaning if you change just like one bit of data, then it should be completely different. And inversibility, and then collision protection, and I do have definitions for all of this. So determinism, a given input message always produces the same hash output. Verifiability, computing the hash message is efficient, so linear complexity, you want this to be able to, what linear complexity means is as the input scales, the amount of time that it takes should scale proportionally with it. So it shouldn't be like if I put in 2, if the input is 2, and then, so let's say 2 squared. This is a nonlinear one, 2 squared. So you'll get 4. But if I put in 8, then that goes up to 16. But what you want is a linear where if you put in 2, it's gonna take 2x amount of time. If you double it, it should take double the amount of time. Might be a little bad explaining. Okay, good. Non-correlation, so like I mentioned, a small change to the message, even just 1 bit, should make it like completely different. So it should be really, really difficult for someone to tell like, hey, you only changed 1 letter in that whole sentence or whatever decide the message is. 2, irreversibility. So computing the message from the hash isn't feasible. Like I mentioned, that's why the elliptic curve function was really, really great, because it's really, really hard to divide, and therefore you can't get the person's private key. And then collision protection. So what a collision is, in the example that we had before, so you see how, John Smith and Sandra D, they both came to the same hash. That is a collision. You don't want that. a good function will avoid that, and so that is a bad function. So, but that is what collision protection means, meaning that so two different messages should never have the same output. And so the hash function that they use in Ethereum is called the, I think it's like KK? I don't know how to say that, but this is a hash function, and it's really popular. It won like it came from like some competition that happened in 2007. There's a bit of a backstory on it, but yeah, this is just the hash function they use. It's a lot more complicated than we actually have time to go over, but yeah. So if you are ever, you probably will run into this if you are programming on Solidity. So Ethereum addresses, we're done here, but Ethereum address, like we mentioned at the beginning, your address is derived from your public key, and your public key is derived from your private key using the elliptic curve function. And so, like I said, you have SEC P256K. You take your private key, input that, then you get what your public key is. Then you use that hash function, and that hash function will create your address, and you use the last 40 characters of the hash function to get your actual Ethereum address. So this is what MetaMask did all in the background. All of this, like all of these different functions, like this one, that's a function, that's a library, meaning that like that's given to you. You can just like call upon that function and use it. And then the SEC, like this elliptic curve one as well, it's given to you as a function. So what really they did with MetaMask is they just took that function, generated a private key, and then got you your address. And that is everything today. I hope I actually kept my time, but we'll quickly walk through some code, and we're not gonna go as fast as we did last time. But for those that have actually written coded before, this isn't like too crazy. It's just kind of getting familiar with the syntax. So there's two different types of data types. There's values and then there's references. So value is like an actual, and you can write all of this out if you want. We also are going to record it, so you can always just come back and watch and get the code yourself. But so there's values and references. So values are data types that actually store like the direct value. So an integer would store either 5, something like that, and then your Boolean will store true. But a reference is more of, it's referencing a different object. So wherever that object is stored in memory. But today we're gonna go over just data types. These are all different data types. So there's Booleans. A Boolean is true or false. And in most languages, like it's either gonna be like bool, maybe you might spell Boolean fully out if you're using Java, if I remember. But bool, so for Solidity, it's gonna be bool. And then right here, you can set it to true or false, the values. And then there's integers. So integers are like, well, we all know the numbers that you count with. And so there's uint. The U stands for unsigned. So unsigned means that it can't be negative. And so the range here, like you'll see, is 0 to 2 to the power of 256 minus 1. And so that is because the default uint is uint 256, meaning like that's the range. So whenever you see anything written like uint 16, what that's saying is take that number and put it to 2 to the power of whatever number is in front of uint. So, but go away. But yeah. So there's different ones. You have uint 8. Most of the times you want to preferably just use uint, the biggest one, just in case like you run into, you might be doing some multiplication and numbers get really big really fast. But if you do want to be very specific and you know you're not going to use a very big number, then it is good practice to specify it down. And it is complicated. Oh, actually before I skip that. So then there's also int. So it doesn't have the u in it, the u, which means unsigned, meaning it's a signed integer, meaning that you can have negative values. And so this is the range. It's a pretty big range, and it's like the same thing. These numbers in the front of the sign just kind of tells you, take that number 128 and 2 to the power of 128, and that'll generally tell you like how many bits you actually have, and or what's the possible range of numbers you have. And so uint, you can have negative, the same thing there. And so it's complicated to just kind of like know all all the types and ranges. So there is a function there's functions and variables in Solidity that allows you to figure that out. So if you want to know the int, you just have to type, and you're just letting it know like, hey, I want to know specific information about this type, and then you have .min, which just tells you what's the minimum value. .max tells you the maximum value. And then another data type is address. So this is a unique feature of Solidity, because with Solidity, unlike most programming languages, you're dealing with, like we mentioned, what we just have our lecture about, is addresses. So when you're writing program, you're writing smart contracts, you're gonna have different people interacting with it, and they're gonna be interacting with your address. So you want ways to store it, ways to specify maybe who owns this contract, who can do certain things. And then last is byte 32. And related to just what we talked about, you're gonna encounter this data type when you're dealing with the cryptographic hash function. What is it? I really wish I could say that name correctly, but yeah, so that one. And so it's just like here, whatever that hash function value is, you're usually gonna store it there and then do whatever you need to. So if you were, I think that would actually be your address. You just talked about use the hash function to get your address. But yeah, you would use that to store. The full hash, and then like we talked about, you would take the last 40 bytes, the last 40 digits, and that would be your actual address. And yeah, I'm gonna scroll down a bit. And so functions are, yes.
Real quick, what does public mean? Like, why do you need that public?
Great question, and we're just about to get to that right here. All right, so public, it just, what the keyword means, it just tells you like what who can interact with that variable or function. So if we go through them, there's different ones. There's private, means only inside the function, and so that means that like you can, if you use it specifically with a function, that means that only any code that is inside, like native to that contract, can call that function, or could call upon that variable. Meaning that this function, this contract, right? This contract it's in its own. Another contract like this value type contract cannot access this add function. And so the way to think about it is our integer u, it's public, so it can be accessed. But if it was private, then no other contract could actually get access to what value is stored there. So, but that's what private is, only inside the contract. And then internal is the same as private, except that you can extend. We're going to talk about inheritance later on, but you can extend and have children contracts, so they have the same kind of like functionalities and maybe variables as the parent. But it's saying that those children contracts can actually access whatever function or variable that you use that keyword for. And so the difference between private and internal is that with private, you can't have any children contract. Absolutely no other contract can. With internal, any other contract that extends the functionality of that current contract is the same. So if I'm not making sense, please ask questions. And so then we have public. They said public is the opposite of private. So inside and outside, practically anybody can access that variable or that function. And then external, same idea, same idea as public, but again, you can have your children contract, which cannot call it. From the outside, only from the outside. No, that's great. I'm glad I read that. So only from the outside, only outside functions can call it. So with external, that is saying that like, hey, this function is not meant to be called inside of this current contract. So inside of function, if I had called this, like I can't call add inside of this, inside of sub. So that's what it's saying. It's saying like, hey, you're not allowed to access this contract yourself, but if another contract wanted to use this function, they could call upon it. And so yeah, any questions on that?
What exactly does the pure signify in the contracts?
Yes, so pure signifies that it's read-only, meaning that you can only read the data or get the value that's returned from this function. So that's what it means. Pure is like pure. You can't touch it, you can't modify it or anything like that. Super specific. keyword there, but it's, you know, obviously you use these keywords to help prevent any errors from the programmer. Yes.
How's view different than pure then?
Great question. Where is? Do we have?
Crypto zombies.
Ah. So yeah. So view is like pure, except they can read state variables and global variables, and we're about to talk more about that. But let me run through this function. But yeah, so that's really about that's really like the biggest thing with functions. You have to write function, and then you write the name of that function, and the parentheses are for you to use capture arguments, and then also you have things like return. So usually this is a bit different than other languages. You have to put the return at the whenever you're kind of writing out the full contract name, and then you also have to signify what type you're returning. And so because you're using those are ints, you're gonna return an int. And yeah. Variables. So there's different type of variables. State variables. State variables are stored on the blockchain. They're variables that are written outside of a function. So any variable that's like written in a contract but outside of the function is a state variable. And that, like, let's say like you run that contract or whatever. You run that contract, you come back a few days later, the same value that was left when you originally ran that's going to still be there because it's stored on the blockchain. So it's permanent, and obviously it can change, but there's always going to be record of that previous value. And local variables are variables that are written inside of a contract, are written inside of a function, and so these only exist when the function is running, the function is executed. So when you call that function, local variable will only be active when that function is called. So like difference with state is if you try to access, so if you get to a contract, you find a contract, whatever, and then you can always access the state variable. You'll always know what that value is, but you will never be able to actually access or know what the value of that local variable is unless that function specifically returns that variable. And last but not least, I'll try to show much, but then there's global variables. So global variables is, if you remember last week when we wrote like that little faucet, we use a thing called MSG, which means it just has information about who actually has information about the transaction that was just called, or the message. And so with that, you can know who the sender was. There's another thing. It also gives you functionalities of, you can also know, you can also just use that to send money to that person, whoever called this contract. But global variables, the way to think about it is like, global variables would almost be close to like those functions we just talked about, like SECP 256, where Solidity just kind of gives you these variables. They're like, hey, everybody, like, you don't even have to implement, you don't have to write them yourselves. These are just given to you. They're global to every single person and everything like that. And so there's different ones. You have sender. So this one stores the address of who called the function. Then you have ones about block. There's the block keyword, which you can use to know the timestamp of the block that's the most current block, or you can use to store like that, or you can use number to know the number of the block. And the beauty, one of the really interesting things about Solidity is that you can actually return multiple variables. So with most programming language, you can't do that. You kind of have to like either create some type of data structure, but they allow you to do this directly, and that's just part of the syntax. And that is everything. So I did go a little bit over time, and we're gonna try to do this. And so we still got about 15 minutes, and I'm gonna break you.